The knowledge of quantum mechanics, combined with Einstein's theories of relativity, has profoundly shaped the modern world. Recent advancements in quantum computing have revolutionized our understanding of black holes, cosmic giants that have long been some of the greatest enigmas in physics. These regions of space exhibit gravity, so intense that not even light can escape, making them appear as one-way traps. However, thanks to groundbreaking quantum computing technology, scientists are now exploring black holes in unprecedented ways, leading to discoveries that challenge and rewrite the fundamental laws of physics. For decades, black holes were considered ultimate destroyers. Anything crossing the event horizon, whether matter, light, or even time itself, was believed to be lost forever. Yet, quantum mechanics suggests a different reality. Information, the fundamental building block of the universe, cannot simply vanish. This paradox has baffled physicists for over 50 years. But quantum computers may have finally provided a breakthrough. The key lies in the mind-bending concept of holography, which proposes that black holes may not be three-dimensional objects as they seem. Instead, they might be two-dimensional surfaces encoding information like a cosmic hard drive, a theory known as the holographic principle. Proving this idea required computations far beyond the reach of classical computers until now. Using quantum computers, scientists have simulated microscopic black holes and observed their information dynamics like never before. These simulations reveal something extraordinary. Black holes do not simply swallow information. Instead, they scramble and eventually release it, offering a possible resolution to the long-standing information paradox. For years, physicists have struggled to reconcile two competing theories: general relativity, which governs cosmic scale gravity, and quantum mechanics, which dictates subatomic behavior. Black holes sit at the intersection of these two frameworks, forming from the collapse of massive stars, yet existing in a domain where quantum effects dominate. Classical physics predicts singularities, points of infinite density where the laws of physics break down. But quantum theory insists that information cannot be lost. If information were destroyed in a singularity, it would violate a fundamental principle of quantum mechanics called unitarity. This conflict is known as the black hole information paradox, a problem that has perplexed scientists for decades. Theoretical models, such as Hawking radiation, suggest that black holes slowly evaporate over time by leaking energy into space, but the fate of the information contained within them remained a mystery. Is it lost forever, or does it somehow escape? Classical computers have been unable to tackle this problem due to the overwhelming complexity of the required calculations, which involve billions of interacting quantum states. Enter quantum computers, machines that process information using qubits, which exist in superpositions of multiple states simultaneously. This unique capability allows quantum computers to solve problems that classical computers would take longer than the age of the universe to compute. Recent breakthroughs have enabled researchers to simulate small-scale black hole analogs, yielding extraordinary insights. These simulations suggest that information falling into a black hole is not lost, but rather scrambled and encoded in Hawking radiation. Scientists at institutions such as Caltech and MIT have used quantum circuits to model how information behaves inside black holes. By entangling qubits and simulating quantum gravity, they have demonstrated that information may escape from evaporating black holes in ways previously unimaginable. These findings support the idea that black holes function like quantum computers, processing and storing information in ways that defy conventional understanding. The implications extend beyond black holes themselves. If information is not destroyed within them, it means our entire concept of space-time must be re-examined. The very fabric of reality may be deeply quantum in nature, with space and time emerging as consequences of fundamental information processing. One of the most exciting applications of quantum computing in black hole research involves wormholes, hypothetical tunnels in space-time that could connect distant regions of the universe. Recent quantum simulations suggest that entangled black holes might behave like wormholes, allowing information to pass between them instantaneously. This could provide the first concrete evidence for quantum teleportation on a cosmic scale. Physicists have long speculated that black holes and wormholes might be intrinsically linked. The ER equals EPR conjecture, proposed by Juan Meldesena and Leonard Susskind, suggests that wormholes Einstein-Rosen bridges and quantum entanglement Einstein-Podolsky-Rosen pairs are fundamentally connected. If true, this means that quantum computers are not just tools for studying black holes, but windows into the deepest structure of reality itself. Recent quantum experiments have provided the first hints that this might be the case. By creating quantum circuits that mimic the entanglement patterns found in black holes, researchers have observed behaviors consistent with wormhole-like information transfer. While still in the early stages, these results suggest that black holes may not be one-way traps, but instead serve as gateways to deeper quantum realities. This raises a profound question. If information is not destroyed in black holes, but instead transformed and released, could future quantum computers reconstruct what falls into them? Some physicists believe that, in time, quantum computers will become powerful enough to decode the information stored in Hawking radiation, effectively allowing scientists to see inside black holes. If this proves true, it could unlock secrets about the origins of the universe, the nature of time, and even the possibility of multiverses. Black holes, once cosmic mysteries, are now becoming laboratories for testing the ultimate laws of physics. For over a century, black holes have perplexed scientists. While Einstein's general theory of relativity predicted their existence, it wasn't until the late 20th century that they became a serious focus of study. The discovery of Hawking radiation in the 1970s raised new questions about their fundamental nature, and now, in the 21st century, quantum computing has brought us to the precipice of answers once thought impossible to obtain. Quantum simulations of black holes are changing the way scientists study these cosmic behemoths by allowing them to model their behavior with unprecedented accuracy. Unlike traditional supercomputers, which struggle with the immense complexity of quantum gravity, quantum computers process information in an entirely different way. Recent experiments at institutions such as MIT, Stanford, and Google's Quantum AI Lab have used quantum processors to simulate black hole dynamics. By creating quantum circuits that mirror the mathematical structures of black hole event horizons, researchers have been able to test theories that were once only speculative. A groundbreaking experiment in 2022 saw physicists use a quantum processor to simulate a microscopic wormhole, not a literal tunnel in space-time, but a quantum system that behaved precisely as theoretical models predicted a wormhole should. This provided strong evidence that the ER equals EPR conjecture might be correct, suggesting that wormholes and quantum entanglement are two sides of the same fundamental phenomenon. The implications for the information paradox are profound. If information truly disappeared inside black holes, it would violate the principle of unitarity in quantum mechanics. However, quantum simulations now suggest that black holes do not erase information. Rather, they scramble it in highly complex ways before releasing it back into the universe via Hawking radiation. A breakthrough 2023 paper from Caltech demonstrated how quantum computers could reconstruct information from simulated black hole radiation. By combining machine learning techniques with quantum algorithms, researchers were able to detect patterns within the radiation, revealing traces of the original quantum states that had fallen into the black hole. This suggests that, with more powerful quantum computers, scientists may one day be able to extract real information from black holes, effectively unlocking their secrets. Perhaps the most astonishing revelation is that black holes might not just store information, they might process it. Some researchers speculate that black holes could function as the universe's most efficient quantum computers. Leonard Susskind has proposed that black holes act as fast scramblers of quantum information, transforming data into highly complex quantum states that are virtually impossible to decode without advanced quantum computing technology. If this is true, then black holes may hold the key to understanding the very foundation of reality itself. The emerging idea that space and time arise from a vast web of quantum entanglements, much like the architecture of a quantum computer, is gaining traction in the scientific community. As research continues, some of the more speculative theories propose that black holes could be gateways to other universes. While this idea remains theoretical, the possibility that black holes are linked to white holes, regions where matter and energy are expelled rather than consumed, remains a fascinating avenue of exploration. Thanks to quantum computing, what was once considered science fiction is now edging closer to scientific reality. The study of black holes is no longer just about understanding the cosmos. It may ultimately reveal the deepest secrets of existence itself. Hypothetical objects where matter and energy spew out instead of being sucked in. If this is true, it would mean that black holes could serve as cosmic tunnels through space-time. But quantum computing has added a new dimension to this discussion. By simulating quantum teleportation protocols on quantum processors, scientists have observed behaviors that resemble wormhole-like connections. If black holes and quantum teleportation are linked, then it may be possible that entangled black holes could serve as cosmic shortcuts, allowing information and potentially even matter to traverse vast cosmic distances instantly. With quantum computing technology still in its early stages, we are just beginning to scratch the surface of what is possible. However, the progress made in just the last few years suggests that within decades, we may have the computational power to simulate entire black holes with incredible precision. Future quantum simulations could help us answer some of the most profound questions in physics. What happens at the singularity inside a black hole? Can we use Hawking radiation to recover complete information about objects that fall into black holes? Are black holes truly quantum computers? And if so, what does that mean for the nature of space-time itself? Could black holes be engineered or manipulated using advanced quantum technologies? These questions, once considered purely theoretical, are now within reach of real experimental exploration. Perhaps one of the most unexpected implications of these discoveries is their impact on philosophical questions about the nature of reality. If the universe itself behaves like a quantum computer, processing information in ways that mirror black holes, then some scientists have suggested that reality may be fundamentally computational in nature. The idea that the universe is a giant quantum simulation has gained popularity among some physicists and philosophers. If black holes are capable of storing and processing information at a fundamental level, then they could be acting as cosmic memory banks, recording the history of the universe in a way we don't yet fully understand. This raises another mind-bending question. If black holes are information processors, could they be conscious in some way? While this idea remains purely speculative, it has led some researchers to explore the possibility that consciousness itself might be linked to the way the universe processes information. If black holes encode and transform information rather than destroy it, then understanding their inner workings could provide clues about the fundamental nature of thought, perception, and reality itself. The study of black holes through quantum computing is leading us towards something even bigger, a unified theory that combines quantum mechanics and general relativity into a single framework. This has been the holy grail of physics for over a century. The discoveries emerging from quantum simulations are providing new insights into the deep structure of reality, hinting that gravity itself may emerge from quantum information processing. If this is true, then black holes are not just mysterious cosmic objects, but rather key pieces in the puzzle of the fundamental nature of the universe. In the coming decades, quantum computers will continue to advance, allowing scientists to simulate ever more complex quantum gravitational systems. This could lead to breakthroughs in fundamental physics, space exploration, and even new forms of technology based on black hole-inspired computation. We are standing on the edge of a new scientific revolution, one in which quantum computing and black hole physics converge to unlock the greatest mysteries of existence. The question is no longer whether we can understand black holes, but rather how deep into their secrets we are willing to venture. For centuries, black holes have been the ultimate paradoxes of physics. They warp space and time so intensely that nothing, no matter, no radiation, not even light, can escape their grasp. But now, a new tool has entered the scene: quantum computers. These machines operate under the laws of quantum mechanics, the same laws that govern the fundamental building blocks of reality. By using them, scientists have begun to unravel the deepest mysteries of black holes. Quantum computers have a unique ability. They can process and simulate quantum systems in ways that traditional computers cannot. While a classical supercomputer would take billions of years to fully simulate the intricate interactions within a black hole, a quantum computer can do it in minutes. As these machines grow in power, they are allowing physicists to conduct virtual experiments on black holes, testing theories that have existed only on paper for decades. At the core of quantum computing is the principle of superposition, which allows quantum bits, or qubits, to exist in multiple states at once. Unlike classical bits, which can be either a 0 or a 1, qubits can be both at the same time. This means they can perform incredibly complex calculations that classical computers cannot handle. To understand how this helps in black hole research, consider one of the biggest challenges in physics: simulating quantum gravity. The equations of Einstein's general relativity describe black holes on a large scale. But these equations break down when you try to examine the microscopic structure of space-time at the singularity of a black hole. This is where quantum mechanics takes over. By using quantum computers, scientists have created models that simulate tiny black holes, ones that behave exactly as real black holes should, but at a scale where we can study them in controlled conditions. These models allow physicists to probe the behavior of quantum entanglement inside black holes, revealing how information flows in and out of them. One of the greatest breakthroughs in black hole physics has come from quantum simulations of the black hole information paradox. Traditionally, it was thought that anything that fell into a black hole was lost forever. But according to quantum mechanics, this cannot be true. Information cannot simply disappear from the universe. Quantum computers have provided a new perspective. By modeling black holes using qubits, researchers have discovered that information might not be lost. It is just incredibly scrambled. Instead of being erased, the data is spread across the black hole's event horizon and encoded in the radiation that it emits. This means that, in theory, a sufficiently advanced quantum computer could decode this information and reconstruct what fell into the black hole. This idea is supported by the concept of quantum entanglement, which suggests that particles inside and outside a black hole remain connected through a deep and fundamental link. If black holes truly operate this way, then they don't destroy information. They process it in ways we are only beginning to understand. As researchers have continued using quantum computers to study black holes, an even more profound idea has emerged. What if black holes are themselves quantum computers? Physicists like Leonard Susskind have proposed that black holes may be the universe's most powerful information processors. According to this theory, black holes function as fast scramblers of information, rapidly converting any matter or energy that falls into them into highly complex quantum states. In practical terms, this means that black holes do not act as simple voids that erase data, but instead as vast quantum systems that encode everything they consume. This idea could completely transform our understanding of both black holes and the nature of computation itself. Some researchers believe that if we can fully decipher the way black holes process information, we might gain insights into the fundamental workings of the universe. These discoveries suggest that reality itself may be deeply tied to quantum information. If black holes are capable of processing and storing vast amounts of data, then understanding their mechanics could revolutionize quantum computing itself. Scientists are already exploring ways to develop more advanced quantum computers by applying principles derived from black hole physics, potentially unlocking new frontiers in computational power. One of the most groundbreaking ideas in black hole research is the holographic principle, which suggests that everything inside a black hole, including space and time, may be encoded on its two-dimensional surface. This idea stems from string theory, which posits that the fundamental nature of reality is composed of tiny vibrating strings. The holographic principle implies that the three-dimensional interior of a black hole is merely a projection of quantum information stored on its surface. Quantum computers have played a crucial role in testing this theory by simulating quantum systems that adhere to the holographic principle. If this idea proves correct, it could mean that black holes, and even the entire universe, are not truly three-dimensional, but instead exist as vast, two-dimensional surfaces encoding immense amounts of information, much like a hologram. Even more astonishingly, if the universe itself is holographic, then everything we perceive as three-dimensional may actually be an encoded projection of a distant two-dimensional reality. This mind-bending concept suggests that our understanding of space, time, and matter may need to be completely redefined. Further supporting this idea is the emerging connection between black holes, wormholes, and quantum entanglement. Wormholes, hypothetical tunnels through space-time, have long been thought to be purely theoretical. However, recent quantum computing simulations suggest that entangled black holes may function like wormholes, potentially allowing information or even matter to pass between them instantaneously. This concept, known as the ER equals EPR conjecture, proposes that wormholes and quantum entanglement are two manifestations of the same underlying phenomenon. If this is true, then black holes may not just be cosmic prisons where information is lost, but instead act as gateways between distant regions of the universe. Quantum computers are now being used to test this theory by simulating entangled black holes and observing how information behaves within them. If these simulations continue to provide evidence for this connection, then wormholes could transition from the realm of science fiction into a fundamental aspect of reality. With every advancement in quantum computing, our understanding of black holes deepens. Over the next decade, scientists aim to develop even more powerful quantum processors capable of simulating black hole dynamics at an unprecedented level of detail. Some of the biggest questions researchers hope to answer include: can we fully decode the information stored in Hawking radiation? Do black holes truly function as quantum computers? Can quantum simulations provide a clear picture of what happens at the singularity? Are wormholes real? And could they be used for space travel? The answers to these questions could revolutionize not just black hole physics, but our entire understanding of the universe. Perhaps the most profound implication of these discoveries is what they suggest about the nature of reality itself. If black holes are information processors, then so too is the universe. And if quantum entanglement governs the structure of space-time, then the fabric of reality may not be composed of matter or energy, but rather of pure information. This concept is central to a growing movement in theoretical physics that suggests the universe is fundamentally computational. In this view, everything we perceive, space, time, matter, and even consciousness, emerges from deep quantum processes operating like a vast cosmic quantum computer. If this theory is correct, then black holes are not just celestial objects, but the key to unlocking the deepest truths about existence. And with the power of quantum computing, we may finally be on the verge of understanding them.